Okay, in this lecture, we're going to continue our investigation of Chapter 14. And this particular lecture is going to deal with how different elements combine together to form chemical compounds, and also how we name those chemical compounds. There's a sort of a set of rules that go into how different combinations of elements get names. And we're going to go over some of those to give you an idea of how different chemical compounds receive their names. So real quickly, let's remind ourselves, an element is a material made of only one kind of atom. So if I have a bar that's made out of pure gold, that pure gold consists only of gold atoms. So atoms make up elements, and the atom is the fundamental unit of an element. In other words, if I take a bar of gold and I cut it in half, I've got two smaller bars of gold. I can keep subdividing those pieces of gold into smaller and smaller pieces. But if I get down to one atom, that is essentially gold. And if I cut that atom in half, if I could do that somehow, I'd no longer have gold. So gold is built up of atoms. Every element is built up of atoms, and that's the fundamental basic unit. Now, when we're talking about the word element here, that's what we're generally using when we refer to macroscopic quantities. So I've got a bar of gold, we say it's an element. But if I look at the submicroscopic, then I'm looking at individual atoms that make up the gold. And so that's sort of when we use one term versus the other term. Now, one of the things that we can do is write down a formula that will show us the proportion by which atoms combine to form an element or a compound. And so in this case, we're going to look at different configurations of atoms that form a single element. And so if we consider oxygen, which is the element O on the periodic table, we've already talked about how it can form O2, which is two oxygen atoms bonded together, or O3, which is three oxygen atoms bonded together. The first one we simply call oxygen. That's the normal kind of oxygen that we breathe in, that we need to live, to do our biological processes. Ozone is a different form of oxygen with an extra oxygen atom. And if you look over to the right here, I've got kind of pictures. These aren't actual photographs of atoms, obviously, but they're sort of representations or models. And so we have O2, where I have an oxygen atom here and an oxygen atom there, and they're bonded together, and they form a doublet of two oxygen atoms making up O2. Now, obviously, if I've got two atoms, they're going to bond together and basically be a straight line. It looks kind of like a dumbbell. But when I add that third oxygen atom, it bonds in a sort of a teepee shape, and you can see that I've got an oxygen atom here, one there, and one there. Now, another interesting element is sulfur, and sulfur, when it combines, it actually has the ability to join together 8 atoms of sulfur, and so you can see it looks almost like a crown. This is representing the sulfur atoms all bonded together. And then, of course, gold is Au. That's the chemical symbol for gold. And gold atoms just basically pack together on top of each other. Now, if we take two or more different elements and combine them together, we create what's called a chemical compound. And so this is a couple of examples here of a couple of different compounds. We have sodium chloride, where I've got, you can see sodium atoms packed together with chlorine atoms. So the little purple ones are representing the sodium atoms. The slightly larger green ones are representing the chlorine atoms. Down below, you can see a representation of the ammonia molecule, the compound of ammonia. Ammonia consists of 1 nitrogen atom and 3 hydrogen atoms. So the chemical formula is, you would read that as NH3. And so you can see the blue here represents the nitrogen atom, and the little white balls, they represent the hydrogen atoms that are bound to the nitrogen. Now, one of the things that I want to mention, because this is an incredibly important point, maybe the most important point of this lecture. When two or more elements combine and form a compound, that compound has completely different chemical properties, or it can have completely different chemical properties from the individual elements that make it up. So, for example, consider sodium chloride. Now, you might remember from your high school science classes that sodium chloride is table salt. It's what we put on our food to make it taste better. And so that actually comes from a combination of sodium metal and chlorine gas. And so when you combine sodium and chlorine and you make them interact and form a compound, the compound you get is called sodium chloride. And here's the thing. Sodium and chlorine, they're not anything you would ever want to ingest, especially chlorine. If you breathed in chlorine gas, it would destroy your lungs. It would kill you. These are very toxic materials, and so you don't want to ingest them, certainly. But when they combine into something that's essentially harmless to be ingested. You can eat lots of table salt and be fine. Of course, if you ate too much, you could have problems. You could, get high blood pressure or something. But the table salt itself is not poisonous, even though the individual components that make up table salt are poisonous. Sometimes you see people who don't understand how chemistry works or how science works using this to make specious arguments. You see this a lot when people talk about the debate about vaccines and whether or not vaccines are safe. And so the so-called anti-vaxxer people, they sometimes use pseudoscience and they say things like, oh, this particular vaccine has mercury in it. Mercury is very deadly. That means the vaccine's not safe. Point of fact, it's not pure mercury that's in the vaccine. It's a mercury compound. And not all vaccines have that, by the way. Only a few of them have that now. But the point is, the compound of mercury with other stuff is completely safe. Just like chlorine gas will kill you if you ingest it, but if you combine it with sodium, it's very tasty and you can ingest it with no problem. So just be aware at how radically the properties of a compound can change compared to its constituent elements. So let's recap. A compound is a substance consisting of atoms from different elements. Compounds have properties uniquely different from the elements from which they are made, and chemical formulas are used to show the proportion by which elements combine to form a compound. In other words, if I tell you that water is made up of H2O, this is one we already know, we know that that's 2 hydrogen atoms and 1 oxygen atom. That is the formula, and it shows you how many hydrogen atoms you have for every oxygen in that water. And so we can see a few more here. We can see sodium chloride is NaCl. Na is the symbol for sodium. Cl is the chemical symbol for chlorine. Ammonia we've seen is NH3. Water is, of course, H2O. And so you can see these different elements combine in different proportions. Here, you have, for sodium chloride, you have 1 sodium atom for every chlorine atom. Here, you have 3 hydrogen atoms for every nitrogen atom, and so on. Now, notice I've been calling NaCl, I've been calling it sodium chloride, not sodium chlorine. And that's because that's part of one of the chemistry naming conventions for how you name chemical compounds. And so here's a basic guide. If you want to read it out, you start with the element to the farthest left in the periodic table. And for the element to the right, you add the suffix IDE. So I'm looking at sodium and chlorine in the periodic table. Sodium is the one on the left. Chlorine is the one on the right. So when I combine them, I want to add that IDE so I get sodium and chloride. And so NaCl is sodium chloride. And of course, again, that's just table salt. Now, there's a second guideline that we can use. When you have different possible combinations of elements, we use prefixes to remove any possible ambiguity. And here are some of the prefixes that we use. Mono means 1, di means 2, tri means 3, and tetra means 4. So here we have carbon and oxygen, but here we've got CO, and here we've got CO2. So how do we distinguish? Because our rule number 1 says we use carbon, and then we would say oxide, but both of these would be carbon oxide by that rule. So, but they're not the same thing. So we want to add something to each one so that we can distinguish between them. And so if there's only one, we use mono. If there's two, we use di. That was from our little table on the previous slide. So we would name this one carbon monoxide. Remember, you get that IDE added to the end of it. And then here we have, again, carbon dioxide. And again, these are actually different chemical compounds with very different chemical properties. Carbon monoxide is actually very deadly to breathe in. If you have a carbon monoxide detector in your house, that's a good thing, because if carbon monoxide builds up in your house, you can't smell it, you can't taste it, you could be breathing it in, and what it actually does is it causes you to suffocate. So it's bad news. Whereas carbon dioxide, that's something we breathe in every day. It's in the air, it doesn't hurt us at all. In fact, we breathe it out more than we breathe it in even, but carbon dioxide is basically harmless. And so the point is that, both of these have carbon and oxygen in them, but because they're different structures, different chemical compounds, they have very different physical and chemical properties. Now here's a couple. We've seen this one before, H2O. The actual name for that would be dihydrogen, because there's two H's, monoxide, because there's one O. And here we have H2O2. That would be dihydrogen dioxide. So these are remember that di prefix means two. So I've got two hydrogens, so I get dihydrogen. I've got two oxygens, that gives me a dioxide. And of course, the IDE is that suffix we tack on to the end. And just FYI, we normally wouldn't call this one dihydrogen monoxide. We'd just call it water. And of course, this one, unless we were needing to be really specific, we generally wouldn't call it dihydrogen dioxide. We would just call it hydrogen peroxide. And that gives us our third guideline here. Common names are sometimes used for convenience. It's much easier to call H2O water than its official chemical name. I think we could probably all agree on that. And so very often, that's what chemists will do. So here is a quick check. We have a combination of carbon and bromine. This is CBr4. How would we name that? Well, if you look at your periodic table and you find C and you find Br, you find that C is to the left of Br, so it goes first. And we know that we're going to add an IDE at the end. And then the last thing we want to do is take care of that 4. We need a prefix to take care of that 4. And if we look at our chart, we know the prefix for 4 is tetra. So which one of these seems to work? Well, hopefully it's pretty obviously carbon tetrabromide. That's how you would name that compound. Now here I have a slide showing you the periodic table, and I'm going to give you a copy of this for you to print out in your modules. It's public domain, so you can just print it out and use it as you need. And this periodic table has some nifty features in it. First of all, if you look at any square, it's going to have lots of information. So number 7 here, if we count up, that's number 7 right over here on the right. It's just kind of blown up. You can see N, it tells you the chemical symbol. It gives you the name, is nitrogen. It tells you the atomic number, What does that mean? Does anyone remember? That gives you the number of protons that it has. Remember, the number of protons is what makes something what it is. So nitrogen has 7, oxygen has 8, etc. So however many protons you have, that's your atomic number. And then down below, you have the atomic mass. And this says relative atomic mass. You don't really need to worry about this. So if what I'm about to say doesn't make sense, don't worry about it. But remember that some elements have different isotopes, and different isotopes mean that they have different numbers of neutrons, but it's basically the same element. And so one particular isotope might have a little bit more or a little bit less mass than the other. And so they kind of do an average. And that's what they mean when they say relative atomic mass. But you can think of the atomic mass as basically, it's just counting up all the neutrons and protons and electrons, and it's all the mass of each atom. Now, if you look over here in the bottom left corner, you can see a little legend that shows you some other symbols. So, for example, this symbol here says radioactive. And so if you look over here, there's several elements: thorium, uranium, plutonium. Those are some famous ones. Those are all radioactive elements. Up here you can see if there's a little teardrop, or I guess that's maybe a raindrop. That's indicating that it's liquid at room temperature. So if I go over here on the right, I can see that bromine is liquid at room temperature. Oxygen, you can see the little cloud that tells me it's gas at room temperature. Here I see a block in the upper corner that tells me it's solid at room temperature. One neat feature of this is that it's color-coded. And so you can see that the alkali metals that we talked about are the brighter yellow. The alkaline metals are the slightly less bright yellow. The noble gases, they're in the orange over here. And so this is a really nice periodic table. You'll be able to find it in the module and print it out, and it'll be good for you to have. One of the reasons why I wanted to go over this is that you'll actually need this to answer some of your mastering physical science questions. So print out your periodic table here before you try to do your homework. Anyway, that's the end of this lecture. I hope you found it useful, and I will see you next time.